Now, we've been talking about translations for a while in the last couple of videos here, but with our investigations and translations, I think with all the work we've done, you've probably convinced now that it is an isometry. That is, that it preserves distance measure, and because of that, it's also a conformal mapping and a linear transformation. It's going to map lines, segments to line segments, and lines to lines. It's going to map angles to congruent angles, line segments to congruent line segments. But we need to formally prove that a translation is an isometry. This is a pretty formal geometry class, anyway, at least my college geometry class is. So, how are we going to go do that? Right? We have to recall by definition, isometry maps a preimage to a congruent image. That's the definition of congruence, right? By our general definition of congruence. An isometry maps a preimage to a congruent image. So here's our proposition. A translation is an isometry, and thus it maps a preimage to a congruent image. So what do we have to prove? We have to prove that if you have a line segment and you translate it, you're going to end up with a congruent line segment. Okay, we can use any of the propositions that we've got in geometry so far to help us with that. So what are we going to do with that? Well, let me just kind of talk you through it, and then I'll show you the formal proof. Let's go back to GeoGebra and hang on just a second. Okay, so we don't necessarily need all that algebra view and the grid and everything, but let's just start with the line segment. And we've got to show that this line segment, AB, is going to get mapped to a congruent line segment, A prime, B prime, right? And so whatever length it is, its image is going to be the same. So let's translate it by this vector. I think it's vector V goes from A to B. So let's just go to let's do it this way. Let's go to the input bar, and down here, it's a little bit off screen for you, but hopefully translate uh, the line segment going from A to B by the vector V. That's 2 to the right and 5 down. I think that's controlled by this. Yeah, this controls left or right. This controls up or down. Let's make it go a little further to the right and a little further up. Let's say it goes up there, for example. Okay, now how can I prove that that is the same, that's going to be a congruent image? Well, what does it mean geometrically for this to be translated? It means that this vector from A to A prime and this vector from B to B prime are the same vector. Well, what does that mean? That means that these two, whoops, not that, that these two vectors here and here, let me go ahead and mark them as, say, red vectors. Okay. That those vectors there are what? Well, if they're the same vector, geometrically, they have to be parallel and the same and congruent, the same distance and the same direction. The direction they make with the horizontal is the same. So they're the same direction. What does that mean? Geometrically, it means they're parallel and congruent. Oh, wait a minute. We know something about a quadrilateral that has a pair of sides that are opposite, that are parallel and congruent. We proved earlier that that has to be a parallelogram. And we also proved that in a parallelogram that opposite sides must be congruent. Therefore, the distance from A prime to B prime has to be the same as the distance from A to B. And there is your proof. Okay? Here it is written down formally right here. Okay? And so that is the proof that a translation actually is an isometry. So for each type of transformation that we do, we're going to need to do something like this that proves that it is an isometry, and thus earlier we had to prove that if it was an isometry, then it maps a preimage to a congruent image, that it's going to map an angle to a congruent angle, a line segment to a congruent line segment, and so forth. Okay? And so, therefore, we know it is distance preserving mapping. That's what an isometry means. And we proved earlier that, well, by definition, really a congruence, an isometry is now going to map a pre-image to congruent image. And we proved earlier that was consistent with our definition of congruent line segments. So that proves that a translation really is an isometry. Next video, going to move on to rotations.